All right. So today gonna be the last day for the class, and I hopefully that people are. So today we're gonna be working on um the final exam review, and hopefully that you guys are um study hard for the final exam. So yeah, so that will be due tonight. I can't grade until most of you finish it, so I can't make the homework and the column for that part. So the homework and classwork gonna be how many percent of that, so you can check them out. And so I believe the homework and classwork will be 10%, right? And I'm sorry, yeah, homework plus classwork will be 10%. So homework will be 5%, and classwork is literally another type of homework problem, so that would be another 5%. And quiz is gonna be 10%. Exam 1 and 2, so each will be 20%, and the final exam will be 40%. So making sure that we have this policy, and please try to complete them as soon as you can. So when I look at the homework problem, it's not so many of them, I believe. So when I check them out for that part, I would say it's gonna be no, I'm sorry, assessment. It's not gonna be a lot of problems. So from chapter 9 to chapter 10. Um, so that will be the most focus that we have. I did not assign homework for chapter 11. Yeah. So if you have any, I would say 1, 2, 3, 4, around 10 problem for each chapter. I'm sorry, for each section. So I teach 3 section at a time. So it wouldn't be a lot of, it would be 15 problem for that part. It will be 2 problem graded, and 9.1s, 8.4, 8.5. So all of that will be graded and will be made of as a single column. And also there will be homework 1, 2, and 3. So those are the classwork problems. So make sure that we submit all of that. So after you submit all the classwork, I'm going to change all the classwork column from classwork 1 up to 5 or 6. So that would be the first homework as well, and so on and so forth. And so that would be due. That would be due I would say that would be to how many classwork have we done so far? So that would be 12. So 12 would be 5% of the grade, and you can check that part. How many points do we have for each classwork? And so I'm going to count 12 of them. So generally, so make sure we do all of them for that part. And finally, that we going to have the final exam review. I believe that we did most of the questions. The final exams, I'm sorry, those are exam 1, exam 2 solutions. So the final exam study guide would be that part. So this is where we're gonna have the final, no, I'm sorry with that. So this is what we have for the final exam review solution. And you can literally click right here and check them, okay? So it should be very, very straightforward problem. If you can do all of these problems and have no trouble doing that, you should be okay on the final exam, okay? So substitutions, evaluate limit using hospital rules, or without using hospital rules. So there are a couple of ways that we can do so. And we also have a certain problem that we need to set up the integral, and this is what we try to get at. For example, I want to set up the area. Area you need to solve for that. We need to solve for that. For dividing the area, I need to complete the entire um, area for that part. For the volume that we do not have to evaluate it. I think you just need to set up the problem just the way that I did. on the study guide, then you get full credit for that. Okay, so, and then population growth, solving the integration by part, I believe those are the things that I put down. And the most importantly, that we're going to have to determine whether the series converges, diverges, instead of the Taylor series, Maclaurin series. Basically focus on Taylor series, especially when it comes to finding the radius of the convergence. So we need to figure it out what value of x they're going to make the series converges, what value of x that make the series diverges. I grade most of the quizzes, and I have seen people never test the equality. That's important. For example, we need to test the equality for that by setting x equal to, for example, this setting x equal to -3 over 2, and +3 over 2, so that you can determine the so that should become a very simple series where we can say directly whether it is divergent convergent without doing a lot of work. All right, so any other question that you have? Any particular problem that you want me to go over? Okay. So, yeah, so if there's no problem, and I don't know what that should do. Yeah, so I'm looking for the problem so that you can ask me how to solve for that, or those are, I checked the solution, it should be correct, almost everything. Yeah. Any other concern that you have? Okay, so I'm not sure if you guys have any trouble. If we do not have any problems, so then we can just stop the review, or I can do like convergence or testing on the radius or interval of the convergence. I might go over finding the terms of the Maclaurin's, I'm sorry, the Taylor series. So that should be a little more interesting with that for the size of x. And I really want to do one more problem for the quiz. I believe that we did. Let me just look at the problem on the quiz and see what's going on for that part. So I would say quiz number 7. And this is the quiz that we have most trouble with. And most of you actually couldn't figure it out on this questions. I believe it wasn't that bad, but the reason why we make a lot of trouble because the center is actually not equal to 0. So we need to use the Taylor series. So for example, that I want you to look for the functions f of x equal to size of 3x. So I want to figure out the integral at pi over 2, I believe. So this is the problem that we have at a equal to pi over 2, pi over 2. So a equal to pi over 2. So this is a problem that I would say pretty difficult for us. So first, we need to write down a Taylor series function where we need to set them up as the Taylor series at 8. So we're going to have f of 0 plus, instead of f of 0, that you have to put the f of a plus f primes of a times x minus a. So this is the part that we need to do so, right? Unless the questions give us the center a at equal to 0, and then we can just get rid of the a. Other than that, you have to subtract the term at the center for that part. So plus the f second point and of a over 2. So remember, this is 2 factorial, so you gotta be really careful. So 2 factorial is 2, but 3 factorial is 6. So this is also a common mistake that people make on the exam. So you got to be really careful when we write them down. Usually, when you write them down the wrong terms, when you simplify this part, then we're gonna make mistakes on it. So, and after that, we keep adding as the polynomial approximation of that function until the end. So we keep going. It doesn't stop at any term. Most of you just give me 4 terms and that's it. No, this is not the correct answers. So 4 term is literally the 0th derivative, first derivative, second derivative, and a third derivative. But let's keep going. It can be 4th derivative over 4 factorial times x minus 8 raised to the 4 power. So it will keep going to forever. So this is what we call the interval approximation. For those of you who study numerical analysis, this is the part that we usually have to do when we try to program a calculator to do a certain calculus perspective, try to compute the area bounded by certain things using calculus perspective. We can use this approximation to evaluate it a lot easier. So yeah. So why do we need to do that? And again, because the questions ask us at the a equal to pi over 2. So the first step that we need to evaluate the f of pi over 2 first. This is where we need to plug that into the psi functions, right? So the psi of pi over 2. So that should be size of pi over 2, and then we're going to plug in size of pi over 2, and we can solve for that answers. So so this is on the third quadrant, right? So this should be equal to -1. But for those of you who do not know what it is, so I do not want to remind you that. I just give you a calculator function you can utilize to evaluate it on a calculator instead of just knowing the rule that all students take calculus perspective. So those are a pre-cal for that part. So we're gonna skip that. But so for those of you who do know what it is, so this is basically located in the third quadrant. So that's gonna make the size negative, so that become -1. So yeah, let me just use the calculator to evaluate it for you guys. We're gonna take the size of, first we need to check the calculator if that is in terms of the radians or degree. Okay, so in this case, it's literally working on the radian itself. So we're going to deal with that, right? So real number, we do have a complex number, and the very famous formulas, which is sine, cosine for that. And but we're not going to utilize all of these functions unless we work for it. So now we're going to go to the size of 3 pi over 2. So the pi will be on this. We're going to hit equal, and then the answer will be -1. So and then we keep going and until we finish the rest of the problem. So, but we need to take derivative for that part. So the f of x is size of 3x, and then derivative of f of x. So so when you derivative the psi, we're gonna get a cosine. So the cosine of psi, so that becomes 3 cosine of 3x. So when we derivative that, the chain rule applies. So meaning that we need to differentiate 3x, and then we're gonna get 3 in the front, making sure that you don't forget 3, because you're gonna keep doing that until the rest of the terms. And then now we're gonna go to the second term that we see right there, and we can literally check that when they plug in 3 cosine of 3 pi over 2, we're gonna get the answer equal to 0. So 3 pi over 2. I mean, we just plug in x equal to pi over 2, right? And then so in order to save us some time to do so, I'm not gonna write them down f of x, f prime of x. I'm gonna just put that 3 pi over 2. So by doing so, I'm going to have the answers equal to 0. At that point, you can check them. So that we get 3 cosines of 3 pi over 2, 3 pi over 2. So you can check the answers that was given equal to 0 for that part. And then we're going to take a second derivative for that example. So we try to take the derivative first and we plug it later on so that we don't make mistakes on it. Right? We can't just tell me, well, okay, so the first derivative is equal to 0, and I take a second derivative, that's going to be 0. No, that is not true. We're going to take the second derivative based upon the function of x, right? Not the value of it. Remember that. So so when I take derivative of -3, I'm sorry, 3 cosines of 3x, that become -9 size of 3x. So we're going to pull out 3 because of the chain rule, and then we change that to the side functions, right? And now we're going to plug that in. F second point would be a pi over 2. And then we're going to get the answers. So we're going to plug in size of 3 times pi over 2, that would be -9. And size of 3 pi over 2. And so the answer for that we can see, -9 times size of 3 pi over 2. And you're going to get the answers, which is equal to 9 for sure. And now we're going to take a third derivative of that part. And so we're going to check this. Would be equal to, so we're going to pull that, that become 27. Cosines of 3x. And we know the fact that 27 cosines of 3 pi over 2, that's going to give us equal to 0 for sure, because cosines of pi over 2 just keep multiplying for that part. So that'll be 3x, and then we're going to do that again. So that becomes f of 3 points of pi over 2, and that becomes 0. So I'm not going to just plug that in and use the calculator to evaluate it. And then now we're going to do the fourth derivative. When it comes to fourth derivative, I'm not going to put down so many dash on top of it. I literally just take 4 on the top, and then I just differentiate 27 cosines of 3x. I got -81. Okay. Oh, I'm sorry, we have -27, and this is positive 81. I apologize for that. So I forgot negative side. When I differentiate from side to cosine, it's become positive. We don't lose out the negative terms. In this case, you're going to be 81 size of 3x, and then so on and so forth. We're going to get to plug in the values of fourth derivative of pi over 2, and we're going to get the answers, which is equal to 81 for sure. Yeah, so the hard part of this problem is we need to plug in the value correctly. So this is actually the f primes, f of 4 primes, and a pi over 2. So now this becomes very straightforward, that I'm going to rewrite a function as a approximations of a polynomial function in terms of the series, right? Infinite series, I'm sorry about that. So it has to be the infinite series. Keep going. It doesn't stop at 4 terms. Just like this question, we only write that a 4 term, but it doesn't mean that it stopped at the term number 4 and then we finish it. It keep going forever. However, when you write them there, we gotta be really careful for that part. The first we're gonna get -1, right? And then the second part, we're gonna get f primes. The first derivative is 0, so the first term is gone. So now we're gonna go to the second derivative. We got positive 9, so that becomes 9 over 2 factorial, right? and multiply by x minus pi over 2 and square. And so the third term will be equal to 0. The next terms, I'm sorry, this is negative, and I apologize. So negative, negative become positive, positive become negative, so that become negative 81. 4 factorial over 4 factorial times x minus pi to the pi over 2 square to the 4 power, I'm sorry. And now we should expect the next term, so that would be 2 times 3, that would be 2, and multiply by 9 one more time. And so we should expect to have the terms. So we have the first 1, 2, and 3. So the next term will be positive, the positive times 9, so that would be 729 over 6 factorial. And so this is the part where we get the terms out. So remember, it is negative, positive, and so on and so forth. And this is pi over 2 over raised to the 6 power. I mean, it keep going forever, but we're now going to put them down. We're going to rewrite the terms with respect from 0 to infinity. And then after that, we observe that this is 3 squared, right? And this is 3 to the 4. And this is 3 to the 6. Okay, so each time that we multiply by a term, 3 to the 6, you're going to check the answer for that. 3 to the 6 is 729. Apparently that we can combine with this. So this becomes 3 to the 2k, right? So, but we have a negative sign in the front, negative, positive, negative, positive. So, so we need to put the negative 1 to the k first, right? Negative 1 to the k. Why we have to put that? Because the first term is negative, the second term is positive. So this is where we started from 0. We started from 0 is k plus 1, I'm sorry. Just want to make sure that with the first terms are negative, and then the second term is positive. And then we multiply by 3 to the 2k, right? Apparently when k equal to 0, this guy is 0. When k equal to 1, this guy is 3 squared. When k equal to 2, this one guy is 3 to the 4. When k equal to 3, this guy 3 to the 6. And then we divide it by k factorial for sure. The bottom is still be like 1 factorial, 2 factorial, 3, 4, 5. So that would be 2k. Sorry about that. 2k factorial. Right, so 2, 4, 6, 8, and so on and so forth. And this part will be x minus pi over 2 and over and rate to the, so square 4, 6, so on and so forth. So that would be 2k. The same thing as the 3 to the 2k as well. So most of you did this questions and missing 3 to the 2k, and you just write out the term without combining all of that. So given by that example, now we can find the radius of the conversion for that part. So the radius of the convergence will be based upon that. It's usually from negative infinity to positive infinity. And so for this part of the question that we need to do this properly for that part. And so in order to figure out the radius of the convergence, so we need to make sure that the, so it's usually, it's vary for, it doesn't matter with the x, so the x has no obligation for that part generally, but we can try them and see whether or not the radius is actually go to negative or positive infinity. So how can we deal with this problem? Are we gonna do the I just rewrite the function with respect to the infinite series from 0 to infinity, and this guy is -1 to the k plus 1. So it doesn't matter what this one just determines a sign for that part, whether the first or second terms. And then we're going to have 3 to the 2k times x minus pi over 2 to the 2k. And we divide it by 2k factorial. And the only thing that we can test this when it comes to the factorial terms is to use the ratio test, right? If you read the book, you can see that they're the root test for that, but it can only be applied when we have all the power. They have a same power for numerator and denominator. If the bottom also have 2k, and then the root test is going to be a lot faster. So the ratio test, we're going to take the limits we call r, right? So that would be the limits of k go to infinity, right? And then we're going to take the ratio between ak plus 1 over ak. And this is a term where we're going to rewrite this. So the first term, you're going to plug in k plus 1. So we have a 2k over there, so ignore -1 raised to the k plus 1. We don't care about this term. This is either positive or negative. The most important thing is where we're going to have the 3 to the 2k, so that'll be 2k plus 1, so that'll be 2k plus 2, because we're gonna factor out the k, and then multiply by the same thing for this, so 2k will be 2k plus 2 as well. So so this is gonna be 2k plus 2. Apparently you're gonna have this terms, and in the bottom part you're gonna get 2k plus 2 factorial, and this is very important. If you write down the term incorrectly, we're gonna get a different answer for that. We multiply by 2k factorial, right? Because we want to flip the entire fractions. So instead of we write them down, we have to divide it by 3 to the 2k times x to the pi over 2, 2k over 2k factorial. I just multiply by the denominator for that. So that'd be 2k factorial over 3 to the 2k times x minus pi over 2. And so this would be 2k. Right. So now how can we simplify this? 2k plus 2, and then we divide it by 2k. We cost them out the bottom part. So first we just need to simplify. So 3 to the 2k plus 2 over 2k, we're going to get 9, right? So 3 squared, we're going to be 9. Multiply by x minus pi over 2 raised to the 2k plus 2 over x minus pi over 2 raised to the 2k. And we're going to get this as pi minus pi over 2 squared, correct? So those terms are positive. You don't have to put the absolute value for that part. And then we multiply by the limits. So those values depend on x. So it does not depend on k. So I can pull them out. And then we only take care of the k factor. And now we need to be careful for that part. So when we write them down, so 2k factorial over 2k plus 2 factorial, and the answer for that would be 1 over 2k plus 2 times 2k plus 1, right? Because they're going to have 2k factorial simplified, so we're going to get those cost out. So this is so this one going to be 0, because when k go to infinity, this is going to be equal to 0. So when the limit equal to 0 times something always be equal to 0 for that part, which is less than 1. And in other words, when the ratio test has the r equal to 0 less than 1, we can claim that it converges. It converges for all x. In other words, the radius of convergence, we can also write them down. The interval convergence would basically bound it between negative infinity to positive infinity. So for this problem, we just write them down like that. Okay. So that's basically the thing that we need to deal with for the first problem. And the second problem, we do pretty much the same thing. So I might want to do it real quick for that part, and so that we can finish the quiz. So for the second problem, x squared e to the x at the center x equal to 1, right? So we need to write them down. The functions with respect to f of x equal to x squared times e to the x at x equal to 1. Right, and the majority of you actually got it wrong. And so we got to be really careful when you deal with these terms. Equal to 1. So we need to test them out using the also Taylor series. I just make the problem really complicated. We can just look at the center x equal to 0 stack. That's going to be easier. It is not easy to differentiate this function by itself. So when we plug in f of 1, when x equal to 1, so we're going to have this is equal to x. And when you differentiate this this function, and then we're going to get this part equal to, so when you differentiate this function, x squared times e to the x, meaning that we need to use the product rule for derivative. So we need to differentiate the first times the second, plus we differentiate the second times the first. You're going to get the same thing right there, times e to the x. And now when you combine them, so when you take the first derivative of 1, so I plug in 1s right there, I'm going to get 2e and plus e. So again, I'm going to get 3e, correct? And so, yeah. And now we're going to take the second derivative of x. Again, that we need to differentiate the function, not the number, not the thing that we plug in. I got one person who just differentiate this, and that's becomes 0. I mean, it's never becomes 0 for the second term. It should be written down in terms of polynomial. So make sure that we're not going to differentiate 3e. You're going to get 3. That is not correct. This is just the number. This is just the value by itself. So we need to differentiate the function like that. So when I differentiate 2x times e to the x, again, that we're going to apply the product rule. So that'll be 2e to the x and plus 2e to the x plus 2x e to the x plus, so this guy would be 2x e to the x plus x squared e to the x. Is literally, we need to add of this. So we're going to get this guy equal to 7, right? So we're going to get this guy equal 7e. And so we plug in 1, 1, 1, 1, you're going to get 7. And then we differentiate the third time. And then we can see that this will be 2e to the x, doesn't change. But when you differentiate this, so that basically you're going to get 2e to the x. So that'd be 4, right? So that'd be 4e. So those two basically 4x some e to the x. We're going to get 4e to the x plus 4x and e to the x plus x squared. So that plus 2x. I'm sorry, it's just some work that we need to do. plus 2x times e to the x plus x squared times e to the x. And so that become 10, right? So this is fixed. This is so I'm sorry, 6 and 6 12, so this guy would be 13, right? So and when we differentiate this, we're gonna get 13. For 1, that would be 13, right? And similarly that we takes the fourth derivative, so you should expect to get, so 3 go to 7, increased by 4, increased by 6, so we should expect to get for the next term, so that would be increased by 8. So when we take the fourth derivative for the entire term, so that turns out to be 2 e to the x, so 2 and 4 will be 6 e to the x, right? 6 e to the x plus so 4x and 2x will be 6x, so that'll be 6x e to the x plus 6 e to the x, and plus similarly to differentiate this, you're gonna get 2x e to the x plus x squared e to the x. It's problematic when you're trying to figure out a term. So and then so let me just combine that so you can easily see them a little bit. So and I plug in x equal to 1 in this case, and then I'm gonna get the patterns right here, right? And so you can check that. You can check that. So we should expect this increase by 4, this increase by 6, and this increase by 8. So we should add up to 28. 21e. So when I combine these functions, we're gonna get 6 and 6, that'll be 12 e to the x, and plus 8x e to the x, and times plus x squared e to the x. Yeah, this is the thing that we have left out. And then we plug in x equal to 1, so we're going to get 12e plus 8e plus 1e, so that'll be 21e. So we can see that the e increased by a number of, so it's just increased by 2 times of that, plus 2, right? So this is increased by 4, by 6, by 8. We can literally, we're going to add 2k's for that part. So we're going to rewrite the functions f of x, right? So the first term would be equal to e, and the second term, we can check them. So that would be 3e raised to the second power, right? And multiply by x minus 1 square. So x minus 1 only. I'm sorry about that. Yeah, so this is, yeah. So I apologize for that. So this is a thing that we have. There's no 2 factorial right there, so I apologize. So I'll divide by 1 factorial for that part. And then we plus, this is 7e over 2 factorial, and multiply by x minus 1 squared, and plus 13e. And yet most of you actually get it here, but you do not really get the forms correctly. And minus 1 to the third plus 21e, and minus 4 factorial, and times x minus 1 to the 4, and so on and so forth. Right, so we should expect to increase by 10, so that would be 31e, and so on and so forth, right? And so anyhow, so this is what you need to write them down. So right, Right. So now we're gonna combine this, and we can rewrite this entire thing from k equal to 0 up to infinity. Right. And so you can see that the terms increase by so plus 2k. So we're gonna have 1 plus 2k, right? Case unit ones. So 0 and 1 and 2 and 3 and 4 and so on and so forth. And then you rate to the e times x minus 1 square. And over, so x minus 1 raised to the power k in this case. So, and then we divide it by k factorial. And then we're going to do the same thing for the rest of the part to identify the radius of convergence. So apparently this function does not converge for the value of x getting big. So it's always be the divergence for that part. So check them out using the ratio rule for this part, and you can finish that. Okay. So any questions so far? So would that be okay? Okay, so any questions? So let me just rewrite it to make it look better for that part. Yeah. Okay, so now we're gonna go for the and any question that you have for the final exam review, and then can check them out for the various convergence or divergence. And so setting up the areas bounded by the volumes and the solid revolving by the volumes for that part. It's going to be a very, very big chapter that we need to review. And by writing that word correctly, and in the hospital rules, when we have the form 0, it's 3 to the 0, or fraction. Remember, the hospital rules can only be used when we're dealing with the form, which is in terms of the limits for that part. Let me just rewrite redo the problem that we have. So it have to be in terms of like, let's say 2x, and we rate to the net. We can't use hospital rule in this case because this is the product. So we need to figure out the way that we can make it as a fraction. So in this case, this is x go to infinity, and apparently that we need to rewrite this in terms of a fraction. So that would be the limit of x go to infinity, and so we're gonna rewrite this 2x over e to the x. Right. So we need to figure out a way that we can deal with that. So if you ask me there another way to solve that without using hospital rule, it might be, right? So we can also deal with that later on. But in this case, so when x goes to infinity, and this has the form infinity over infinity, right? So in other words, that we need to take derivative for both numerator and denominator, which turns out to be 2 over e to the x. So now when x goes to infinity, what's going on for that part? When x goes to infinity, the bottom will also be go to infinity, but the top is not infinity. So the entire thing's go to infinity, which is undefined. So you can check the problem for that part. So the bottom is equal to infinity. So we have 12 over infinity, so that's going to be 0 for that part. Yeah. 12 over something really big, so we're going to get a limit have to be equal to 0. Okay, so it's really important that we can set up the bound correctly. And if you ask me, there is another way you can do it. There are actually more than one way to solve that problem, or you can take a look at that and try to make it as the entire fraction, and then we rate to the power x. So we try to make it using the squeeze theorems or anything like that, and so that we can bound this function by 2. So this bound it by 1 over e to the x, for example. And so this one, the limits go to 0 for sure. And you can also bound it by I would say, so this guy also bounded by, so you can pick a function that's gonna make this terms equal to 0. So we can make any function for that part as long as that is, so we can go to like 2 to the x, 2 to the e, right, and raised to the x. So we remember that this one is less than 1. So we have a to the x, a less than 1. So when you have a less than 1 and something that go with a really big power, so that turns out to be equal to 0. You can try any number. So you can try something close to 1. So we get 2 over e, right? 2 over e was basically less than 1 for sure. We can try them out on the calculator in this case. So where's the e term? I don't see them. So I need to figure out where my e is on this calculator.
E to the x is where ln is.
Oh, e to the x by 20. There's another e. I just forgot what it is. I know this is e to the x is 1. So it should be less than 1 for sure. Let's say we take 0.7. I can take 0.99. Even something that is less than 1 is work. 99, and then the rate to like 10,000 power, right? So x is really big. No, it's actually equal to 1, so it doesn't work. Yeah, so it doesn't work for this case. Actually, something that is close to 1, the rate to the big power should equal to 0, but for not so sure. So let me just do it again. 0.9999, and the rate to the something like that. So is it close to 0? Yeah, it's actually close to 0. So my power is not big enough. So let's say we take the really big x. Let's say a million, a trillion for that. And then we take something that is close to 1. I mean, like 2 over e is actually not close to 1. Yes, I found an e right there, and it's actually rate. And then when you rate to like 10,000, and of course it's going to go to 0. So by using the squeeze theorem, that we can know the fact that this 1 go to infinity, of course that goes to 0, and 2, this guy is 2 to the x, right? So remember 2x is of course less than 2 to the x for sure. There's no doubt it. And then so because the ratio is less than 1, so what's the squeeze theorem can bound this function, and that is basically equal to 0 for the limit. However, that we going to have like a certain questions. Let's say we have x to the x to the form, and this is have to bring it to the e to the x form. So this is something that we learn it at the very beginning of semester, and this strategy is really, really important. That we going to, so we instead of we taking the limit, right? So remember, you can't just say something like x to the x, 0 raised to the 0 is 1. So this is not correct, right? So making sure that 0 raised to the power 0 is not equal to 1, right? So it might be, but remember, where x go to 0 plus, so 0 positive, right? So 0 plus. So let me try on a calculator. Let's say we take 0.00001 and 0.00001,
and it's rate to the something that is close to 0 as well. 0.00000001, is it equal to 1? Yeah, it's actually equal to 1, but you cannot explain it that way generally. But remember that sometimes you can bounce it. You can bound the we can bound the x that is something that is um, can you find me a number? Can you find me a function that x to the x is greater than that, and uh, that is go to 0 for that part. Um, I'm sorry, go to 1, and then and find that function. I can try e to the x. I know e to the x is basically go to 1 because x is less than e for sure, right? X less than e. Um, because x coach 0 for that part. I can try like 0.001. No, it doesn't work. So sometimes this function is really hard to use the squeeze theorem, and you have to think of it and find me another functions for that part. And maybe we can test with any polynomial function, and we subtract that. It's basically positive, but it's really hard to differentiate this. So there's no way we can do so, and this is not the way that we can apply the hospital rule directly because it is not in the form of the f of x over q of x. So remember, the hospital rule only worked for a fraction, where it's have to be in the form infinity over infinity, 0 over 0. If we have 1 over 0, that doesn't work. 1 go to infinity, or 0 go to 0, right? So this is where we need to apply the hospital rule in this case. And apparently that we can take the limits where x go to 0 plus. And so we're going to take the e, right? So we're using a very important characteristic, which is e to the ln x equal to a. Just any a. So I take a as x to the x, right? So I can also rewrite x to the x as e to the ln x to the x power. So the whole point of doing so, remember, the whole point of doing so is trying to bring down the power. When we bring down the power, we can try to make this as a fraction. As simple as that. So because I can't, there's no way we can change this to the, there's no way we can bring down the power in this case. So unless we take the ln for that part. So apparently that we're gonna evaluate it. We're gonna interchange the limit part. So we're gonna put it on the top of it. And so in order to stop the confusion for that part, I'm gonna take e raised to the power something for this. So this is e. So this is e raised to the power of ln x to the x, and now I can bring out x times ln x because I can put that power. Now, so this is the product is good, right? Why the product is good? Because any product I can just rewrite them by making it a fractions, right? So remember that we can make that to the fraction. So this one turns out to be e to the limits of x go to 0 plus. And so remember, we can't apply hospital rules right away because it has to be in terms of f of x over g of x, right? It has to be in terms of a fraction before we can differentiate them. So now we need to rewrite them as ln x over 1 over x. But why not the other way around? So the reason why we cannot rewrite the other way around, if we put ln x on the denominator, it's gonna make the fraction really complicated. So let's say you want to differentiate 1 over ln x. So we need to use the product rule and so on and so forth. We still have to have the ln x term at the end. So that makes the problem more complicated. It's not make the problem simpler. So in other words, that we need to take the limit where x go to 0. And so now we can apply the hospital rule. So because I know the fact that when I differentiate ln x, I got 1 over x. When I differentiate 1 over x, remember, when I differentiate 1 over x, I'm just doing it fast. So we're going to get negative 1 over x squared. So when I divide it by negative 1 over x squared, meaning that I multiply by negative x squared. So now the entire term turns out to be, so this still be the e to the power something, e to the limit of x go to 0 plus. Now this becomes negative x, and apparently that this go to 0 when x go to 0 plus. So remember that it's positive, and that turns out to be e to the 0 equal to 1. So you can't claim that. So I can try to compare them with the square theorem, but it's really hard to look for the function where x close to 0 that is bounded by two functions that is close to 0. It's not possible. I mean, it's not impossible. It's going to be really, really challenging problem to do the limit part without using hospital rules. So hospital rules came in handy when we try to evaluate a certain problem that require some of the derivatives. So same thing for this part. You can see that we can use the hospital rule immediately because when you plug in 1, it has to form 0. Plug in 1 has to form 0, and then we can take the limit for that. There's another way that we can do so. There actually another way, so we can try it, but we're not gonna try in this example. So it takes some time to do so using the square theorem. Similarly, you can factor it out and plug in 1, you get 1/2. And for that question number 6, you can literally check that when I plug in negative 2 is not equal to 0. So we're not going to use the hospital rule for that part. So it's become 4/8. And then I just simplified them equal to 1/2. That's simpler. Okay, that's very simple for that. And similarly that we can plug in x equal to 2. So size of 2 pi equal to 0. And x squared minus 4x plus 4. And when I plug in x equal to 2 there, you're going to we also get this form 0/0. So meaning that we can apply the hospital rules by differentiate this in the bottom. And then we keep doing that. We have to differentiate twice so that I can get 1/pi squared. And notice that the cosize of 4 pi, when I plug in 2 there, so that become cosize of 4 pi, which is equal to 1. And similarly, we can use the hospital rule for that part for most of the problem. And most of the integration derivative that we learn is literally coming from the second exam. So where the first part that we need to use the, this is complicated. Actually, this question was on pretty much on the second exam, except for the fact I'm taking the ln of cosize of x, right? So this is pretty much the same thing as e of x cosize of x dx. And we can utilize that by using by using integration by part twice. And then you definitely gonna solve for that, which is I equal to ex sine x plus ex cosine x over 2. So the only thing that makes it different is that we need to integrate twice for that part so that I can keep the I, as I call I on that integral. So this is pretty complicated question. That is pretty simple question where we just literally differentiate using integration by part by setting u equal to ln x. So whenever you see a function that go with the x and ln x, then we have to set u as ln x. When it comes to the functions where we have x and psi or x and e, so then all we have to set u as a function of x. So we can deal with that completely. So it's the same simple strategy for that part. And similarly that we have for this part, again, get it solved. So some of the function will be required to identify whether or not it is defined or not defined, or improper or not improper function. So let's say we take a look at question number, this one is really important. So I really want to point them out where it's 0 to 2. And what we have from the function was, this is 3 over 15 minus 6x. So if we change the question to 0 to 3, then we have a big problem because the function will be undefined. So in this case, it's good because we need to figure out the domain of the function. So we take 15 minus 6x not equal to 0, right? So meaning that x, so we're gonna solve that simple inequality. And then we're gonna get x is not equal to 15 over 6, which is 5 over 2. So 5 over 2 is not in between 0 and 2, so we're safe to evaluate it. Remember, if I change the question to 0 to 3, then we have to split them down from 0 to 5 over 2, and then from 5 over 2 to 3. In this case, that we don't have to split because it is not in the range between 0 to 2. So we're good to go. So this is just a proper integral, so we don't have to care much about that. So remember, when we evaluate an integral, we need to make sure that this is proper. If this is improper, then we cannot evaluate it. We cannot evaluate it when you look at a function. So you gotta be really careful for that part. So for question number C is good because it doesn't really give us any boundary between A and B. But for question number B, you gotta be really careful, but we're lucky that x is undefined. The function is undefined at x equal to 5 over 2, which is good. However, when you look at this guy, so this guy good. So when you look at this, so the function's basically bounded between 1 and 2 for t over 1 minus t squared dt, right? So from 1 and 2, t squared over 1 minus t dt. So apparently that we can see them. This is not defined. So remember, t's have to be different from 1, right? So apparently that we can't literally just integrate them and figure out a final answers. So we're gonna do some work for that part. We need to subtract them or differentiate them for this part, and we're gonna get the final answers correctly. You can use, I'm sorry, t over 1 minus t squared. So I apologize for that. So this is t over 1 minus t squared. So we can use the chain rules or whatever it is. Some of you might break it down in terms of 2 fractions. That's perfectly okay as well. So this is improper. This is improper function, right? Integral. So if this integral evaluate from 2 to 3, then we're good to go because it is not bounded by 1. So it is perfectly okay. So for that integral that we need to, so we can break it down in terms of 2 functions, which is a over 1 plus t and plus b over 1 minus t. You have different way of solving this integral generally. You don't necessarily have to work on it and check what it is. But my suggestion is that when it, I just simply use the chain rule, so I just combine this to become 1 and that's going to be a lot simpler. So I want to take the u equal to 1 minus t squared, right? So by doing so, when I differentiate the u, I'm going to get negative 2 t dt. So I actually got the term t dt out. And the only thing that we need to get rid of would be negative 2. Some of you might just solve for dt by du over 2t. which is perfectly okay for that part. So the entire integral will be, turns out to be du. So we're going to have -1/2 in the front over u in this case. So that become ln of -1/2. And then we're going to have 1 minus t squared. So we need to evaluate it from 1 to 2, right? So remember, when we evaluate from 1, we need to set it as a. And then we take the limit for that, right? So there's no way that we can plug in 1 immediately. So we can just need to evaluate it by 2 first. So we're going to get -1/2 of ln of 3, because we have to be positive. So when you plug in 2's, there'll be 1 minus 2 squared, so that'll be 3. And plus 1/2. So we're going to take the limits where the limits go from when the a go to 1, right? So we have to set it up as a, and then we're going to plug in ln of 1 minus a squared. So when a go to 1, apparently that this guy go to infinity, and on this going to diverges, right? For sure. Okay, so apparently most of this question are going to be like that. Okay, so far so good. Any other questions? I'm pretty much done. I'm not sure what question that you have. If you ask me the question, I can help you. You problem. If you don't ask me the question, then there's nothing I can do. Okay, for secants, also improper integral, because secant squared, secant is 1 over cosine, and it's undefined as pi over 2. So generally, even if we can't, it's sort of, so we know the fact that this guy will be tan, right? We notice the antiderivative for secant squared will be tan, but when we do so, that we can't really get the finite answers properly, even though we can figure out a tan of pi and tan of 0, so very easily, right? And however, you sort of, well, it's going to be 0 for sure, but no, it is actually undefined because it's not bounded at x equals to pi over 2 for the secant. So you got to be really careful for that part. Okay, so if there's no more problem, then I would call it a day. All right. Any other concern? Any questions being asked? So if there's no more problem, then from the last question we did, what was the answers? Which one? From the last questions, I'm not sure what your last question is. This one, right? Yeah, this one's diverges, undefined. So because we cannot find any number that is, so the limit when it's a equal to 1 is 0. ln 0 is undefined when you plug in something that is close to 0 for that. So we can take the ln, can check them. So 0.0, it's going to be really, really big. It becomes really, really big for that part. So ln of 0 will be 0. I would be undefined, I'm sorry. And 1 is 0, so quick. Okay, so that's not going to work for any value for that part. And apparently this is not going to be the case. So the most important thing also that we need to know, how you're going to set up the integral correctly when we want to rotate it around the x-axis, right? Using a washer. So that'll be pi of v of pi of r square, outer square minus the inner square, or shell. So it has to be with respect to y because it's rotating around the x-axis. So that'll be 2 pi x. So in this case, that'll be 2 pi y times the top minus the bottom. So that'd be, so the x equal to 2 is on top of it, and 2x squared are going to be on the bottom part. And so when you do so, we're going to take the top, subtract the bottom, and we're gonna get this ones correctly. Similarly, it's rotating around the y-axis. So when you use the Washer method, then you have to solve for a y to look for the inverse function of that, and then we have to integrate them respectively with respect to y. For the shell method, then we just need to integrate them with respect to x from 0 to 2, so that would 2 pi x times the top subtract the bottom. So the top is 2x squared, the bottom is 0, so that would 2x squared right there. So we're gonna get this done. So this one is a little bit difficult because it's not bounded. It's when a function is not bounded, so you gotta be really careful when you try to find the solid generated by this. So in this case, we can literally check when we use the Washer method. So when we use the Washer method, the rotation will be around the x-axis, right? So we can literally check this curve. So this is not a solid bound from 0 to 4, right? So we need to, from 0 to 4 is bound between these functions and the curve y equal to 0, which is the x-axis. So from 0 to 4, we're going to have to take pi r squared, which is pi of x raised to the 2/3 square, and plus the pi from 0 to 8. I'm sorry, from 4 to 8. So this is bounded by two functions between x to the 2/3 and y equal to x minus 4. This is where we need to subtract them. So this is apparently that the outer is x to the 2/3, and then the inner is x minus 4, and so from 0 to 4, from 4 to 8. But when we use the shell method, it's basically more likely we doing the circumference. So the circumference is not affected by this one, so it's perfectly bounded. So the circumference is literally work perfectly all right. So we just literally need to take from 0 to 4, and for the y. So remember, when it comes to the x-axis, when we try to use the shell method, it has to be from 0 to 4 on the y-axis. So then we're going to have to deal with 2 pi y. So because the curve rotating about the x-axis, and so 2 pi y, and then you can literally see that the outer in this case, so we rotated x, so it has to be something like that. So it's going right here, and we can literally check this sign is x minus 4 is going to be greater than that. So that become y plus 4 and minus this curve, which is x to the 2/3. That become y to the 3/2 on dy, so you can deal with that. And similarly, it's rotating around the y-axis. Y-axis has nothing to do with this bound. For the Washer method, it's easier. We just basically take the so around the y-axis. So well, I mean, usually the final exam does not. You don't have to solve specifically for any method. So let me just take that example in there. Let me just copy and paste. I'll take that example. So I'm going to copy this page. Okay. Great. So if I ask you to do this function around the x-axis, and of course have to be about the x-axis as well. About the x-axis, right? So apparently that we can check that this going to be really complicated, right? Because when it comes to the x-axis, you're gonna have something like this to deal with, right? So we have to split the curve into 2. And so when we use the shell method, right? So the rotations had to be going like this. So it's rotated. So it's split into two parts, right? For the Washer method, so for the Washer method, it's complicated. Washer method is complicated. Complicated, right? So what I can do for that part, so when I do this with the Washer method, I have to split them up. So the Washer method have to be into the pi A and B, depending on if rotations around the x or the y axis. So the outer square minus the inner square. So the outer, I put the r square, right? The inner will be the functions with a small r, and have to be dx, right? So that rotation split that into two parts, right? So for the Washer method, you can literally check this. So from 0 to 4, so you have to deal with the x, right? Have to deal with the x for the Washer. Have to deal with the x. Deal with x for Washer, right? And so for Washer, that we need to do from 0 to 4. And we can check this literally about it from 0 to 4. So this is only the x-axis and the curve. So the function that we have is x equal, so this is y equal to x to the 2/3, right? And this is y equal to x minus 4. So apparently we can check them that this one is literally, so the r square that we have will be x to the 2/3 square. Of course, we need to simplify that. And minus, so what is the outer, so the inner function is this one, the x, y equal to 0. So we don't care much of that. This is the curve y equal to 0, right? So this is for the Washer. So I'm gonna use different color for the Sharrow method later on. So minus the pi r squared. So in this case, is from this is where plus. I'm sorry. So this is bounded by two functions, right? This is bounded only by one functions, right? One function, because this is not a solid bound, so we have to split them up, right? And this is by two functions, by two functions. So if you have a function like that, it's easy. When you have a function like that, it's easy. Just like this, and it's bounded by another function. So those are the solid bounds, so there's no gap between them. So if they want to evaluate it from 1 to 5, for example, right? It's easy, right? You can use either Sharrow or Washer method for that. It's clearly what we have. But when it comes to the function like that, it's bounded. But though there's a gap between 0 and 4, so this is not bounded by the function y equal to x minus 4, so we cannot take that into account. We only take that bound from 4 to 8. So this is where you can see that the curve is cut. So this is the lower, and I'm sorry, this is the inner, and this is the outer. So for that part, then we need to take the x to the 2/3 square minus x minus 4 square. Okay, on dx. Yeah, this one is relatively difficult to do so. But now we do the same thing using Sharrow methods. The Sharrow method is simpler. So that we going to take the rotations around this, right? We're doing the circumference for that part. So around the x-axis, so we're gonna do like all of this circles, the circumference, right? So all we need to do for that circumference is remember the Sharrow method that we're going to have a formula, which is around the x-axis, that have to be 2 pi y, right? And we're going to have to do with r of y, with respect to the function of y. I usually use the height for that part. Circumference times the height, and so that would be h, which stand for the height, minus the small h, which stand for the height of the small height for that part, and dy. So around the x-axis, so you have to be something like that. So we can deal with that, which is 2 pi, right? So it doesn't matter about the gap right there because it's going here. It's going around this, right? Around the x-axis. So we do the circumference part of it. So that become y. So we need to solve for this function with respect to y. So we're gonna get x equal to y to the 3/2. And this guy, when you solve for x, would be equal to y plus 4. And for that questions, we can literally deal with that by taking, so we can literally check that the outer in this case will be equal to y plus 4. And we're going to take that y plus 4 and minus y to the 3/2. And in this case, we can also get this done perfectly for that questions. And that's pretty much a thing. It doesn't matter. I don't know in what kind of thing that we need to deal with. The only concern that we need to deal with is pick the right method in this case. So in this case, that we need to integrate with respect to y from 0 to 4. So similarly for about the y-axis, we do the same thing. We're gonna get the same answer like that around the y-axis. So for the Washer method, it's easier because around the rotation about the y-axis, the Washer method doesn't care about the bow here that we perfectly okay to deal with. But for the shell method, that we need to split that up into 2 parts again, and then and so on and so forth. So that's pretty much the thing that we need to deal with, right? Any concern about chapter 7 or chapter 9 and so on and so forth? Okay, so if there's no more concern, I would call it a day. I hope you guys are going to study really well. For the population, just got to be careful when you use the formulas y equal to y0 e to the k. I mean, that's pretty straightforward, but you know, solve for that and so on and so forth. It's sometimes a little bit challenging for us, but so this is the entire course, and I hope that you guys are going to be doing really well on the final exam on Wednesday. And that after that, we're now going to see each other again. So today is going to be the last day that we see each other in Zoom. When it comes to the final exam, I post it, let you know the time, just do it and submit it. And so when you start it, just finish it in 5 to 6 hours. And after that, I'm going to grade it and let you know the grade. So again, today is going to be the last day that we see each other in Zoom. You need additional hours for the review, let me know. Other than that, I wish you best luck on the final exam on Wednesday. This Wednesday, not next Wednesday. If you miss the date, then you're gonna miss a lot of information. You know, just please do it today because the final exam, you miss the final exam, you're gonna wait out until August something, August 8 or August 15, I don't quite remember. So before you can make up the final exam, but you have to pay for that though. You have to pay for like $50 for one exam. So, all right. Anyhow, this is the things that we have in the final exams. And I wish you guys are going to be doing really well. Okay, so have a great day.
Good one, Professor.
Thank you, Professor.